Hey guys, it's Bob Morreale here with the Tuning School, and on today's Tech Tuesday, I'm sitting with Jim Gray from Venom Racing Engines, and we're going to be talking about how to properly build a bottom end for forced induction. Hey guys, welcome back. I'm talking today with Jim Gray from Venom Racing Engines. And Jim, thanks for being willing to sit down and talk with us, man. We appreciate it.
Absolutely. Thanks for the opportunity.
Absolutely. So Jim, we have a lot of questions that we've gotten from guys who've been watching the Forced Induction series. And everybody wants to know how to properly build a bottom end for the purpose of forced induction. So the questions are, from left to right. We've got a pretty fair amount of them. Before I get to the questions, let me ask you, Jim, tell me a little bit about your history.
Well, I started off loving race cars the first time I ever heard an engine run, especially with open headers.
Yeah.
And it just kind of ate me alive. So whenever I was a teenager, I started building engines locally for people, and I teamed up with a guy in Mountain Home, Arkansas named Alan Hood. And Alan was a great teacher to me whenever I was younger on block machine work and engine packaging. And we worked together for about 3 years or so, where he did machine work and I did the assembly process. And we gained a lot of customers that way. And eventually we ended up teaming up, and we joined forces and ran a business together called Hood Performance Racing Engines, which Alan is still at now. But then after that, I moved back to the St. Louis area and really wanted to stay in the race engine business, but time didn't allow at the time, and I ended up in the aerospace field. And I was contacted by Rankin Technical College about heading up their high performance racing department. And I went on there and I taught high performance race engine machining and building and tuning for about 5 years. And then leaving there, I found a wonderful opportunity of a man that was retiring that had an amazing race engine machine shop with all top quality equipment, and was able to purchase it. And man, our doors have been just flooded with mainly boosted and nitrous engines of all sorts.
That's awesome. That's awesome. And you get some boosted and nitrous. That's really the best kind, right?
Oh, definitely. I like them both. I ran Outlaw 10.5 myself and limited 10.5, and been an avid drag racer for most of my life, and so I like them all. But I like circle track engines. I like anything. If it's a max effort type deal,
yeah,
it's what I like.
Going fast. That's why we like you, man.
Exactly.
Jim's, you guys built our engines for our Trans Am we use to teach classes with here, and it's forced induction. And we've always enjoyed talking with you guys. Really highly competent guys over, whether you're at Rankin or where you're at now. So, Jim, let me just kick it off with some of the more simple questions we've gotten from some guys, and I don't know, maybe the shop owners have to field this a lot. Is there a huge difference when you're building a bottom end for forced induction with we'll call it a budget forged build versus a really high end, you got a $2,000 crank or whatever you want to call it, versus something that's kind of more budget for the average guy, for the street and strip kind of guy?
Yeah, there's a great deal of difference that goes into those, to be honest. The mild builds, like 10 psi and under on boost, you can do a lot of times with stock bottom end parts. But what we found, depending on the manufacturer of the engine, the connecting rods are usually the weak link. They usually give up 600 or 700 horsepower or so. They start to fail. We found that a lot of the stock rods they'll actually kind of kink and lay over in the cylinder where they have a slight bend to them. They'll keep running that way, but they start scuffing the pistons. We had one recently that was a LSA GM deal that had the exact same problem, and it laid over far enough that the piston skirts were actually hitting the counterweights on the crank, and you could hear it whenever you were outside listening to it. And we tore it down, and that's what it was. So the answer to that is anything that if you're trying to make that much power or more, forged internals are an absolute must. And there's a lot of variables that go into that, which we can talk about however you'd like.
So if you're, let's say you're a guy who's going to run 10 pounds or less, basically a street strip kind of guy, what is it okay for those guys to buy the less expensive forged parts?
Yeah, absolutely. Now we use a lot of the less expensive forged parts in atmospheres like that, where the boost is not real high.
Okay.
Just aftermarket connecting rods of some kind and a forged piston of some kind is great. All of those will handle, up to about 10 pounds of boost, or maybe even a little bit more. We have guys that push them a lot farther than that, but I always try to sell good quality, not a lot of volume.
Right. So if you're going and you're kind of higher than that to begin with, or maybe you have big plans, What's the most critical parts when you're building it? Say you're going to go 20 pounds of boost, 25 pounds of boost, or maybe, maybe a little less boost and 100 shot. What's the most critical stuff? Is it still the connecting rod? Is that what's taking most of the abuse?
The connecting rod and the pistons at that point, because there are several different piston materials and shapes that you can end up with. And I always try to look what a customer is going to end up with. If he has the intent of building an engine that's going to run naturally aspirated for a few months before he can afford to put the supercharger or the turbos on, I always look down the road where we're at, because the cylinder clearance, the piston to bore clearance is really critical on a high horsepower engine, where it's not near as critical on an NA setup. Also, the same with the connecting rods and the bearing clearances. So we always try to look down the road what the customer is going to have, because the last thing I want is give him something that he thinks he can get by on now, and then 6 months later he's put a 98 millimeter turbo on it, and he's bringing me a bucket back that I could have prevented.
You don't want that.
No.
He's a member of that exclusive club. What's it called? DOTC, Drive Over the Crank.
Yeah, I have seen a lot of them. I try to stay completely out of there.
Yeah, that's not a membership you want to join, right?
Oh,
no, it's really not. So when the guy calls and says, I need you to build me a forged engine, and I'm going to put a blower on or a turbo on, what are the basics that you start with? Do you say, okay, man, we need to start on the side of figuring out compression? Do we need to start on the side and work your way down from there to the parts? Or how does that work for you?
It's kind of a progressive process. The first thing, obviously, is usually a person's budget. So I usually try to get a feel of what they want to spend. And I tell people this all the time. I try to sell good parts to make good engines, because we actually make more money when we sell less expensive parts. So I try to sell the more expensive parts because they're better for what the customers get. But what we start off with is find out what their budget is, what we can fit them in, and then guide them in how much they can do with that budget. And then the first thing that I always go to after that is what kind of fuel the customer's going to run. Are they going to run pump gas? Is it going to be race gas? Is it straight methanol? Are they going to meth injection with water? Or, there's a lot of variables there, because that's going to determine how much compression ratio we can go with.
Okay. Now, you mentioned the pump gas, race gas, and meth injection. And when you're looking to build one versus the other, let's just start with pump gas versus race gas. What does that do for you in the decision-making process?
It just tailors where we leave the compression ratio of the engine and the nature of the parts that we put in.
Okay.
A person that starts off knowing they're going to run race gas, we usually put better parts in there, because they're probably going to use them more.
Understood.
If we build something that we know they're going to run 93 octane on, and there's a chance they might put some meth injection on it, we back it off and make it to where it's it's going to live in whatever they do with it. So tailoring the compression ratio is the main thing.
So the compression really is. And is there a sweet spot that you find? Maybe there's just one versus the other. And let's say LS platform, for an example, that really tends to have longevity and give you good power under forced induction, where you're not giving up too much of one for the other.
Yeah, there is, but there's a lot of variables that go there, because the engine sees a lot of dynamic cylinder filling that's tied to the camshaft that's really more important than just the static compression ratio that we can calculate. So there's a lot of variables in there, and it also depends on the tuner, because a lot of tuners will tune things that run a lot of ignition timing, and if I know the tuner and I know that they run on the heavy timing side, I'll back the compression ratio off a little bit to to match that. If I know that they're a conservative tuner, I'll be okay with bumping it up. But usually between 10 and 11 to 1 is where we try to stay at, even on the forced induction stuff. Mm-hmm. The LS engines especially, they have good quench. They really work efficiently when they're there. Mm-hmm. And we've had no problems running 10.7, 10.8, even with boost, like with the LSA superchargers and stuff like that. We've had really good success with those.
Wow, that's awesome. And I think maybe a lot of guys watching it will go, wow, because they're used to forced induction builds somewhere in the 9 to 1 range, if I had to guess.
Yeah, and that used to be the theory, but there's a lot of efficiency comes from compression, and there's also a lot of power when the boost is not present that's there. The engine will feel stronger when it has a little bit more static compression ratio in it early, before the boost is actually applied. But it's tied directly to the tuner. If a tuner, gets carried away and tune stuff like he did when the engines were 8.5 to 1, and
sure,
might not have as much success.
Totally understand that. I get it, because when I first started, we were on Buick Grand Nationals, and those were super low. I want to say they were like 8.5 to 1 compression, but the old technology from the 80s.
Oh, definitely. I mean, we do twin turbo methanol stuff now that's 13 to 1 with a lot of boost on it.
Wow, that is awesome. That's crazy. Have you guys played at all with coating on the piston tops or skirts or anything like that?
We have, and we use the armor glide coating that some of the manufacturers use. It works. It works pretty good at anti-scuff. The hard anodizing we do if the engines are running on methanol. I found that to be a great benefit. It helps the corrosive, agent on top of the piston. And it also helps with the scuffing. I found that the skirts look a lot better with the hard anodized stuff when they're loaded heavily. As far as any type of Teflon coating or anything that's on the piston skirts, it depends on the cylinder bore finish whether it's even beneficial or not. If we do it, we finish the cylinders really fine depending on the rings that there are, and they seem to last a while. But I've seen the Teflon type coatings on the piston skirts be gone after 5,000 miles, depending on.
Wow.
So there's some variables there too.
No, and I'm not an engine builder, so I don't know. This may sound like a really stupid question, but a lot of guys want to know, is there a different grade of component where you're seeing failures a little more, a little less, and you're going, man, this is it. You need to use this.
Yeah, the place that I would say that I found that is in pistons.
Okay.
And they have changed over the years so much that it's hard to nail down exactly the cause. But what I found the cause is the piston material. In the past, most forged pistons were made from 4032 alloy, which the silicon content in 4032 is really high. Pistons don't expand that much. That being said, you can run them a little bit tighter in the bore and they handle heat better. The only problem with that is that since they are that way, they're a little bit harder, and they don't take the continual abuse when you get at really high horsepower levels, as well as like the 2618 alloy does. 2618 alloy doesn't have near the silicon content in it. It expands a lot more, and you have to allow for it in the bore clearance, so we would run more bore clearance on it. But the piston will take a lot more abuse. If you start to detonate it or whatever, it will handle it and not come apart. But the 4032 or the harder alloy of forged piston, a lot of times if you see minor detonation under booster nitrous, it can break the ringlands in there because the material is actually harder.
Right.
So that's definitely a failure point. If it's something that's going to make some serious horsepower, then we usually go with the 2618 alloy.
Right.
And build it basically like a race motor because the pistons will handle more.
That makes perfect sense. So you might even take the same approach for a guy that is going to run 87 octane when he leaves.
Yeah, you could. The only problem is that the 2618, it definitely fatigues faster, and it doesn't have as long of a life. The 4032, you can put in a street car and it lasts a long time. The 2618, it's kind of race car maintenance. It doesn't last as long. So there's a give and take there.
That makes perfect sense. Now, we're kind of talking along the lines of materials at the moment, and one of the questions we had from one of the guys on Facebook was, is there a preferred material for rings in a forced induction application? From maybe rings, pistons, rods, but in this case, he really was talking about rings.
That's a good question. And again, it really is application specific, but I'll give you my opinions on what I've found with it. For years, ductile type rings, ductile iron type rings with a coating on them were what people use. In fact, they still use them in a lot, and we use them a lot. For example, like the plasma moly top ring. Ring seals really well, takes between a 280, 400 degrees or 400 surface finish on it, with the stones, and they seal really well. But the problem is that at certain horsepower levels, or if the clearances are too loose or the engine sees detonation, the moly coating starts to flake off of them. So that being said, we've really switched to running steel type rings that are coated, and they seem to handle the power greatly. The only thing that I urge people to do if they buy their own parts is to look at what type of steel rings you're running. I've seen customers come in and have stainless steel rings to run in regular cast bores, and they will absolutely destroy a bore. So some sort of nitrided steel ring for the top ring is my pick on it. The second ring, if we build the engine here, then I like to run the Napier second rings on things. They control oil really well, but they're very finicky on assembly process. That's why I say if we assemble them here,
right.
I don't like to sell them to customers if they assemble them out there, because if they don't have the proper tools to assemble them, they 6 out of 10 of them end up breaking the Napier lip off of the rings and they fail. But that would be my pick on a forced induction deal. I would want a nitrided steel top and a ductile second, whether it's a Napier or not.
Wow. Now, that's really good, because I can see some internet buyers or eBay buyers doing exactly what you said not to.
Yes.
I would imagine that's really common. Another question we had from a guy on Facebook, a shop owner on Facebook, wanted to address clearances, bearing clearances, clearances in the rings. How is that in relation to a naturally aspirated engine, for example?
Well, it's greatly different, especially in the rings. But it also depends on the type of piston. The piston manufacturers have designed the tops of the pistons, the crowns, and the ringlands between the first and second ring to handle different areas of boost, but that ties right into what the ring end gap is. So I like to run a little bit more ring gap and allow things to expand than some people do. But we use ring end gap factors for pretty much every application, whether it's a certain amount of boost or a certain amount of nitrous. That's the main thing, though, is that that you need to have more ring gap to allow it, because it's not that the amount of power is what gets it; it's heat expansion. If you put a lot of nitrous, for example, on a stock engine that has really tight clearances to start off with, the rings will expand too far, and the ring end gaps will actually butt together. And when they do, the combustion force is literally trying to push the piston through the ring that's locked up in the cylinder, and it does what we call lift the ring lands right off the top of the piston, and then you have failure, and it sounds like it sounds like somebody's beating the engine with a hammer.
We have seen that way too many times. Mostly Dodges, the late model Hemis with the thin ringlands, man. Guys with turbos and blowers on a bottom end that's stock. We see them. When we used to have it in our shop we used to own, we would actually diagnose our Dodges that come in 6 months after a build, or after a stock bottom end with a blower or a turbo put on. What we would do is we'd pull the catalytic converters and shake them out. And then rings would fall out. And we're like,
really?
We know where the problem is. Absolutely. Because I'd imagine they're just super thin from the factory.
Oh, yeah. Yeah, well, and they run pretty tight gaps, too, from the factory. Everything in the blocks are CNC machined now, so you can run things tighter than you used to be able to with older style engines. And that's why the stock bottom end craze is kind of hit and miss, especially with like the GM 5.3s, which are really crazy. I mean, you see guys that are spraying 400 and 500 horses of nitrous on these stock bottom end 5.3s, and it's about 50-50 whether they work or not. You'll find some of them that have a lot of wear in them. The clearances have opened up where they'll handle it, and some of them are still tight, and they just don't. So it's kind of a funny deal.
So what you want, if you're building a good nitrous motor from a stock GM motor, is a old, wore out 200,000 mile truck motor.
Well, kind of. Kind of. Yeah, you want one that the rings are still working.
Right. Okay. All right. Details like that. Yeah. All right. So how about bearing clearances and such?
That's probably my favorite topic of all that you can discuss when it comes to that. I've spent 20 years of my life trying to learn the bearing clearances and where they work in different applications. And the bearing clearances are directly related to the power level and the oil viscosity that you want to use. So I always encourage people when they're going to have a build is to find someone that has experience in doing that. The rule of thumb on bearing clearances for a performance engine is you need 1,000th of bearing clearance for every 1 inch of shaft diameter that you put in the bearing one. Now that's a generalized statement, but if you stick with that on most things, you can usually be successful. So if you have a 2-inch rod journal on the crankshaft, then 2,000ths usually will be a good amount of bearing clearance, for most performance applications. The more power that you make, the more heat expansion that you're going to have. The higher the RPMs you have, the more the heat expansion, and you have to allow for all of that. So the bearing clearance thing is it's probably the biggest key that a lot of people miss, and it's also dependent on the material that you're using. One thing that I always tell people, if you use an aluminum block, for example, GM, if you have an LS1, 2, or 3, then they're a cast aluminum block, and they're really flexible. And they require running clearances pretty tight on the bearing clearances because they expand so much. Aluminum expands nearly twice the rate of steel. So if you have a cast iron block, you're going to have to allow a little bit more bearing clearance in the beginning because it's not going to expand like the aluminum does. So it's really important to have someone build your bottom end that knows how to properly check the clearances and set them where they need to be. And it also, if you use an aftermarket block, they're more rigid. You can get away with running things sometimes a little bit tighter there because the block has less flex in it through the range.
Makes perfect sense. So now moving down a little bit to the rods, the connecting rods themselves. Another question we got was I-beam versus H-beam, and is there a time and a place for each?
Yeah, I would say so. I mean, in a lot of the connecting rod manufacturers can manufacture the H-beam connecting rods to handle a really good amount of power for less money than the I-beams. The I-beam rods, most of them are forged into shape, and the outsides of our machines are kind of made like a forged aluminum rod used to be, and they're more expensive to make like that. That's what I've been told by the manufacturers anyway. But the I-beam rods, I usually prefer them in maximum effort engines whenever you're making the most horsepower that you can. It's the step right before stepping to aluminum rods. But the H-beams, they're the best bang for the buck for pretty much every manufacturer. I mean, you can put a set of virtually anyone's H-beams if it has good bolts in it, and have pretty good success if the clearances are right. I won't mention any names, but we have ran here for some people doing research and development. We have ran some really inexpensive H-beam rods at some astronomical power levels with great success. But we pay really close attention to the bearing clearances on them. There are a lot of engines that we go to great lengths to make sure that the clearances are right. But what I usually do is in a budget, mild build, H-beams of any kind are great. And then if it's going to be some sort of really high horsepower with a steel rod, then I usually go with a billet I-beam style of some kind.
And do you ever see anybody doing the Z06 route with titanium stuff?
Very few. I mean, we have some. It makes it difficult to balance the cranks because they're so light, so you have to do a lot of work. And most people don't want to go that way.
Right.
But I have seen a few. We've done a few like that.
And I'm sorry to interrupt you.
Okay.
I had a guy telling me, it was a couple months ago, I was talking with a guy at a trade show, and he was talking about how most of the balanced cranks that he finds are not really balanced.
Right. That's true. In fact, I just had one that we did the other day that was a customer brought in and switched directions, and everything was supposed to be, as ready to go. And I always check things. I won't put my name on it unless we check it. Even if I have to eat some of the labor, I have to check it. And we found the crankshaft was way off from where it was supposed to be at. Most people make a mistake when they'll buy rotating assemblies to put in these engines, and they assume that they come balanced. Now, from some of the manufacturers, you can buy them and they will state balanced assembly at the end of the part number, and they will be balanced when you get them. But if you just look up in a catalog and pick up a rotating assembly for your application, it's going to come target balanced. For example, the 4-inch stroke LS engines usually end up around 1800, 1810 bob weight with flat top pistons or so. The crankshafts will come in usually target bob weight balanced around 1850. That's a lot of out of balance condition. And I'm not saying that they won't run. We have customers that have done it. We won't do it because that 40 grams of force is thousands of pounds of unwanted force against the bearings out of balance when you're at high RPM. So I encourage people to always research what rotating assembly they're buying because they don't always come balanced.
That makes perfect sense. And in terms of other clearances, maybe it's Ringland depth or thrust and things like that, is there anything else that's super critical when you're looking at building an engine, regardless of a performance? Like maybe you have a cheaper crank or a very expensive crank?
Yeah, definitely. I mean, as far as the Ringland clearance goes in the pistons, there's a lot of science there, and not a lot of builders won't talk a whole lot about it because you make mistakes as you build engines and you find out what works and what doesn't. And the Ringland issue, a lot of people assume that you need to have the rings just as far down as you can if you're doing a forced induction or a nitrous thing, which part of that is true. But there's a lot of other variables. If you end up with the Ringlands and the valve pocket in the top of the piston being close, you can end up with literally no material in between where the intake valve pocket is and the Ringland cuts through, and I've seen them just burn through because people miscalculated when they ordered custom pistons. On a naturally aspirated engine, the higher you get the rings up in the piston, then the more stable it usually is, because the lower you move the ring down toward the middle of the piston, the more the piston teeter-totters. And when the piston can teeter-totter, the ring becomes an oval, and it doesn't seal very well in a round hole. So that's kind of where we are with that. But the big thing that I always look at on forced induction engines is you want a good amount of material above the top ring. I like to see 250 plus above the top ring, but I also like to see well over 100, close to 150 between the top and the second rings.
Okay.
And a lot of these builds, you have to be careful with how thick you run the rings to get it there. You have to run pretty thin rings on some of them to get them there.
Yeah, that makes perfect sense. And is there a certain, I don't know if I want to say brand, but is there a certain style or type that is better at that than the others?
As far as pistons go, or rings?
Pistons.
Well, any of them, if you get them custom, they'll make them however you want.
Right.
But pretty much all of the manufacturers now have switched to either a 1.2 millimeter top and second ring or a 1.5 millimeter top and second. Okay. And both of those are plenty acceptable to get some good ring packs. Even in a 4-inch stroke engine like an LSU, you can still get a good ring pack.
That makes
when they used to be 1/16 rings or 5/64 rings.
Right. Yeah, that makes perfect sense, because if you're the average shop owner or enthusiast watching, and you're looking at it going, okay, what do I need to know in order to buy the right pistons? And most of the time you're hearing, okay, I got to get the compression right. And yes, that's true, but it sounds to me like there's more than just get the right compression. You also need to look at the Ringland gap and things like that.
Absolutely. Because the distance between the rings and whether the piston has anti-detonation grooves and anti-scuff grooves, the area reduction grooves above the top ring, all of those play into what the piston will handle. So, sure. And along with the material, so it really helps to do your homework or to trust a shop that specifies in that field, so that you can end up with a successful product and not be
sure.
redoing it again.
And not be picking up or a member of the Drive Over the Crank Club, as we like to call it.
Exactly.
Absolutely. Well, hey, that's all the questions we had today. Thanks for chatting with us, Jim.
Absolutely, man. It was my pleasure. I really enjoyed seeing you again, and love talking to your audience.
I think we need to get out and get the drag strip to take the Trans Am out or something.
Man, I'm in. You let me know when, and I'll make a trip down.
Absolutely. Well, thanks for chatting with us, buddy. Have a good day.
All right. Thanks, Bob. You too.
All right.